Good evening. Welcome you to the KLA's second annual Water Quality Summit. I'm Tim Sellers, and obviously I am not here in front of you. I'm very sorry that I can't be in front of you today. Unfortunately, I had some issues, some family issues that came upon, and not here. But I did want to make sure that I at least got my information out tonight because this is a really important event. And it's great to see so many of you, and I'm assuming that I could see so many of you. uh, my part of this evening is to talk about the lake ecology, the current status of Keuka Lake, and touch upon some of the recent events and threats. But it is only a prelude to a lot of really great information that will come after me from great speakers who I can only assume are actually there in person. I know they're going to be talking about a lot of great details, some of which I will introduce and touch a little bit on, but the real magic comes in with their talks, with Tony and Marie and other people's talks there. And selfishly, I'm sad that I won't be able to hear those directly myself. So moving into this, I hope that the volume is okay and you can hear everything sufficiently. Very briefly, I am Tim Sellers. I am the Associate Provost here at Keuka College, and I've been here for a number of years. I'm also a Professor of Biology and Environmental Science at the college. I started the Center for Aquatic Research here, so that's sort of the founder and the director. I also make the coffee. It's not a big group. In terms of my background, I have my undergraduate in University of Colorado in environmental science, and then a master's and a PhD from the University of Louisville in Kentucky in environmental biology. I've trained as a limnologist or a kind of an aquatic biologist, and have been fortunate enough to conduct research in a variety of different aquatic environments, from lakes, rivers, oceans, probably even a puddle or two. Specifically, I'm a systems biologist. I put together sort of mathematical models generally of how aquatic systems run, and I typically focus on the very small things that no one can see with their naked eye. That is the plankton and how they work. We're going to talk about a number of different things tonight, me and the other speakers. And in order to get a better sense of these important topics, we want to talk a little bit about, first, a little bit of the lake ecology. I'm not going to give a giant lecture here, but just give you some sense of what makes lakes different from, say, oceans or rivers, and how that will translate into some of the issues and opportunities that we'll be talking about tonight. In general, a lake is kind of a static system, especially compared to something like a river. The Mississippi River can be just as big or bigger than Keuka Lake, but it's moving, it's flowing, it's going downhill essentially. And so all of that water is very well mixed in the river, top to bottom, bottom to top, side to side. Everything kind of happens. Generally you can take a scoop out of the Mississippi River at any point, shallow or deep, and you're going to get about the same thing no matter what. Same temperature, same organisms, lots of stuff. Lakes, in contrast, do something we call stratify. And so if we take a lake and we're able to slice it in half, so we can see the surface of the water and we can see the bottom underneath, we know we've got shallow parts and deep parts. Well, in contrast to that river, the lake is pretty static. The water really isn't flowing that much. Now, it does flow. We know Keuka Lake flows. It has an inlet and outlets. Has a few inlets, one in Branchport, one in Hammondsport, and multiple smaller inlets with the little creeks and ephemeral streams that exist throughout the lake. And it has one major outlet, and that's in Penn Yan, and where the lake then flows out through the Keuka Lake outlet and ultimately into Seneca Lake. And while that flow is there, it is nothing like the river or even the high energy of some oceans. So lakes do something we call stratify, and the sunlight is coming from the surface. It warms those top waters. Those top waters absorb most of the light or the heat, and that means that the light and heat doesn't get down to the very bottom. Consequently, the upper waters will go and warm up fairly quickly in the spring and early summer, and the bottom waters will stay pretty cold. But unlike a gradual drop in temperature from the surface to the bottom, this stratification is, as the name is, very strata, very layered. The surface waters, we'll say about from the surface down to about 30 feet, and it varies, but in that area, remain about the same temperature. We call that top layer epilimnion. So it's, let's say, 75 degrees at the surface, and if you go down about 10 feet, it'll be about 75 degrees, and if you go down another 20 feet, about 75 degrees or so. It's fairly well mixed and certain there. But then you get to a very radical change point, and we call that the thermocline. And instead of having a very gradual change in temperature, you get a very dramatic and quick change in temperature in terms of depth. And you go from, let's say, 75 down to 40 degrees in a matter of 12, 15 feet. It's a very, very quick temperature drop. And so we tend to think of lakes as having these layers or strata, and we say the lake is stratified. That top layer, which we call the epilimnion, is going to have warm water. It's going to have well-lit water because that's where the light is coming in. And the bottom water is going to be generally darker and cooler, but with that very strong thermocline or layer that divides the two. Tonight we'll be talking about a lot of different issues with Keuka Lake and the water quality. But probably the one thing that they all have in common in some way is algae, and algae that is growing in the lake. First of all, there's a lot of different kinds of algae. If we look at, there's algae that grows on the bottom. You might see the slimy stuff next to your docks or growing on the rocks or the dock pilings. And then you've got another algae that are microscopic, usually unicellular or very small little things that are suspended in the water column. So they're not growing or they're not attached to anything, but they're throughout the surface of that water. So that's stuff that grows in the bottom, and then the suspended stuff. The suspended stuff we generally call phytoplankton. So that's plankton that is plant-like. And this algae, or this suspended algae, phytoplankton, in generally is a really good thing. In fact, it is the base of the food web. The way that the algae grows is the way the lake grows. We can't have fish without having this wonderful phytoplankton. Probably hundreds of species in Keuka Lake alone. Each a little different lifestyle, different preference, but essentially they have the same job. They photosynthesize. That is, they turn the sunlight energy into sugar energy, like any plant would do. And with all of that sugar energy, then small animals eat them, and bigger animals eat the smaller animals, and fish eat the smaller animals, and we go on and have a wonderful food chain and food web. And the phytoplankton sit right there at the base and make it all happen. Phytoplankton are very good, and because they photosynthesize, they want a few things. They'll generally like to have warm temperatures, and they like to have a lot of light to do their job. Consequently, they live in that top layer we talked about, in that epilimnion, just above the thermocline, for the most part. Now, Keuka Lake also has some phytoplankton that lives below the thermocline. That's kind of a unique situation, not totally unheard of. Skinny Alice, for example, has something similar. But in general, if you look at all lakes together, it's a fairly unique property that Keuka Lake has. Tonight, though, we'll probably be focusing most of our time on the algae that is in that surface layer, the good stuff and the bad stuff. Well, Now that you know everything there's ever been to know about lake ecology, haha, let's jump in and briefly touch upon what we know about Keuka Lake and how we've come to gain that knowledge. The KLA has had a very strong sampling program for well over 25 years that has focused on looking at a variety of different parameters on Keuka Lake, throughout Keuka Lake, shallow water, deep water, and so forth. We've kept this primary lake sampling process pretty much the same for those decades. We've added some tricks to the protocol, but we've kept a lot of the same things. So we've got a very strong data set going back, many decades, as I said. Generally, what it looks like this: the volunteers, many of which are in the room tonight and do the real work, they will on a sampling day will do everything. We'll take all the samples they want in one day. Usually, it's about a half day to do it all, top to bottom. They do that day sampling usually 5 to 8 times a year, usually once a month. They'll go out and do that all there. And so we've been doing that for a number of years. What that day looks like is actually taking samples at 16 specific sites across the lake. The actual locations are denoted by those red dots on the right-hand side on Keuka Lake picture. You see there's not quite 16 dots on there. Those are the locations. The 16 sites include some are deep, some are shallow, so you could be at the same physical location and one sample is a shallow water sample, and then another sample is a deep water sample at that same location. So you get, at the end, you add those up, you get about 16 sites. They're evenly distributed across the lake, so all three of the branches, the east and west north side and the south branch. We do near shore samples, so those are close to the banks. We do a lot of open water, so it's primarily in the middle of the lake between the two shores, and shallow stuff around a meter deep. And some of the deep water ones, which typically are around 30 meters, and we even have a few some plankton samples that could be even more than that. We know that by doing all of these different samples, one thing that has been pretty constant through time is that we see very little variation north to south or east to west in the lake. Typically, what's happening in Hammondsport on a given day is what's happening near Branchport on that same given day. Kind of interesting. And I'm always interested to look and see if there are these variations in location, but not so much. What we look for are various things. Some of the biggies we do are nutrients, so things like phosphorus or TP, nitrogen or this nitrate. Those are two of the primary drivers of algal growth. Then we measure the algae itself using primarily chemical techniques to measure the amount of pigment they have. We call it chlorophyll A. We measure how turbid or how clear the water is using a Secchi depth, which is almost like a dinner plate suspended on a string. And we do a lot of other things like pH and conductivity and temperature, of course, to round out what we're gathering from the lake. So jumping into some of that data that we've collected, what we're looking at here is a graph over a course of 25 years or so, even more long, almost 30 years, from about 1991 until last year, 2018. And this is looking at the average phosphorus concentration in the lake. Now we take 16 samples, so we've averaged all these things, and we've collapsed a lot of the data. So some of the interesting stuff is sort of hidden within there. But we're showing a general decrease in the amount of phosphorus that's in the lake. Now, phosphorus, as I said before, is what we call a nutrient for phytoplankton or algae growth. Typically, the more phosphorus we have, the more algae we could have or tend to have. We need to have some, but we don't want to have too much. And when we look at lakes across the world that have lots and lots of algae problems, by far the biggest driver of algae problems is the amount of phosphorus they have. We have lots of phosphorus dumping into a lake. You're going to have a lot of algae and probably too much, and too much of the wrong kind. The good news for us is over this last 3 decades or so, we've seen a general decrease in the amount of phosphorus that we have in Keuka Lake, and that's primarily attributed to wonderful watershed practices that the KLA really has been driving in education of its lake constituents. So we're doing a lot better in how we use fertilizers and agricultural processes, which is the primary place where phosphorus tends to get into a lake. So good news on that. Another piece of data is how clear the water is. So you can imagine if there's a lot of algae suspended in the water, it'd be really green and not very clear. Conversely, if you have very little algae, then you would have very clear water. And for those of you who know and love Keuka Lake, generally we've got very clear water, and that's backed up by the data. A similar time period in this graph, what that red line is showing, it's a generally moving up. That's a good thing. What this translates into is the water is becoming more clear over time. So less phosphorus, and the water is becoming, the water clarity has increased, or clear water, which is great. All those blue dots are those individual data points that you can see. And if you really look at it, you can see that there's sometimes where it's very clear and sometimes where it's not very clear at all. But that red line kind of averages out, so we can see general trends. So looking at phosphorus data, looking at water clarity data, and what's really the fulcrum between those things is the actual amount of algae. So, which we said we measure by this one chemical analysis, chlorophyll A. So if we've got a lot of chlorophyll A, we got a lot of algae. Again, a similar time period with our x-axis, or that horizontal axis. And you can see in this case we're looking at bars, not dots, but the same thing. That generally we're seeing a downward trend. So the average amount of algae in the lake has been going down over these 25 or more years. 2018, that red bar in all these cases, that red one is that last year's data, is no exception to showing that lower overall value. It's a little higher than a few of the ones previous, but still in a pretty low section, and definitely lower than the long-term average. This all stands to reason. All these three graphs, the lower phosphorus going down, if there's less phosphorus, then there's less amount of algae that has the possibility of growing, and if there's less algae, then we should have clearer water. So everything really makes sense in this very surface level view of a lake ecology. Now, the last three graphs looked at trends over multiple years, almost 30 years. This next set of graphs are looking at what's going on within a single year, 2018 in this case. What did it look like when we started measuring in May, and then through the summer, and then to early fall? How did these things change? This graph is looking at phosphorus. And you can see there's two lines. One is the amount of phosphorus that we were measuring in the deep water samples we did. That's the solid line. The dotted line is the amount of phosphorus that we were capturing in our shallow water samples. You can see there's a lot of variation, some up, some down. The shallow and the deep seem to track each other for the most part. No great deviations there. And it doesn't seem that we have any real up or down over the year. We've got some ups and downs. There's some seasonality, which we suggest mirrors what's going on with some of the other organisms. But overall, nothing too dramatic in this one. This is the same 2018, and we're looking at the amount of algae, the chlorophyll A. And when we look at this, we said there's many, many species that this all encompasses. We're all kind of jumbling them up together. So in this data are the majority of the good species, and we're capturing some of the bad species, like some of the HABs and or blue-green algae that we'll talk about more in my talk, and certainly in the talks to follow me. So this is really just kind of pulling everything together. In contrast to the phosphorus a minute ago, we can see that our deep water algae levels are usually lower than the surface water, or those dashed lines. And that generally stands to reason from general lake ecology that we're finding more algae in the shallow parts in that epilimnion than we would find very deep. So that makes some sense. Also, the deep is a little more steady in terms of its variation across the year, where we see more peaks and valleys, more dramatic peaks and valleys in the shallow water samples. In terms of numbers we're talking about, these are both very low. So we're looking at chlorophyll values anywhere from around 1 to maybe at most 4. When you compare that to something like Honeoye or Seneca Lake, then you're looking at values, chlorophyll values, let's say in the 10s, 20s, 30s, 40s. So orders of magnitude greater. Now we're looking at nitrate. It's another one of those nutrients for those algae growth mechanisms or foods, similar to phosphorus. Nitrogen typically isn't as reactive for algae as phosphorus is, but that's not all the case. Algae, just like you and I, need nitrogen and phosphorus to live. And in terms of some of the things we're looking at, and particularly in terms of our blue-green algae, cyanobacteria, there are a few signs that maybe nitrate is going to be more interesting than the phosphorus that we see. In this case, if you squint, you could maybe say that the nitrate levels are going down over the year, and perhaps, though there's a lot of variation around that, as you can see with some of those error bars. And we don't see a great difference between deep and shallow layers. But one thing you do see is that generally the shallow samples are lower in nitrate than the deeper water. And there could be some good reasons for that one, especially if algae are really finding that to be a driving force. Looking at each of these individual pieces, the algae levels, the phosphorus, the nitrate, and they tell little different stories. And sometimes we want to kind of pull all this information together, and along with things like water clarity and other parts, and say, okay, at the end of the day, what's this really mean? How do we kind of get a summary of this? And one way to do this is looking at trophic statuses, and that basically says, well, let's take our phosphorus, our chlorophyll, our how clear the water is, and we'll take those numbers and crunch them down into one index number. In this case, we call it a Carlson index. And that then allows us to do some comparative studies between this lake and other lakes, or how this lake has changed over time. And that's exactly what we're seeing here is Keuka Lake over about 25 years, that same kind of time range we looked at before. When you put all this information in there, similar to what the other data suggested, so no surprise here, we're seeing a decrease in our trophic status. And generally what we're looking at is the lower the trophic status, the healthier the water is. And that's generally. We want to have phosphorus, we want to have algae, we don't want to have a swimming pool. So the very lowest part of a Carlson index could be a swimming pool. And when you've got really no nutrients to grow algae and no algae there to take the nutrients, we call that oligotrophic, and that's that bottom layer. And you can see that's where the lines have been trending towards. The middle layer we call mesotrophic. That's where you've got more chlorophyll, more phosphorus, generally more turbid or less clear waters. And then at the top of that index, you'd have something called eutrophic, and that's when you've got really high algae. So something like Honeoy we would consider most of the time as being eutrophic. Uh, Lake Erie often is in that eutrophic component. So much algae, so choked in there, it's not good. So this, going along with our decades data and even our within year data, really suggests that Keuka Lake is in a good spot. And I think as a good summary, that is a good spot. We have most of the parameters that the other lakes are quite jealous of. Uh, we really truly have a gem of an aquatic system here. But we're also here tonight because it's not a highly polished gem, at least not now, and we have to be very careful. Of course, this unpolished gem is the reason why probably the majority of people are here, or at least the most interesting part of that. And that has been our more recent outbreaks of blue-green algae, or more technically, our cyanobacteria. And I know that Maria and Tony we're going to give a lot more information about this, so I'll just barely touch on it. What most people see are these beach closures. And we've had in the last 3 years now. What you're looking at on the left-hand side is I think our first beach closure of this year, of 2019, where the Red Jacket Beach and Park was closed because of this blue-green algae. What the picture you see sort of on the right-hand side is something very recent that was sent to us at the KLA. As part of our program that Maria and we'll talk about, where residents have captured this information, in this case pictures, and said, hey, something doesn't look right. And I totally agree. Something doesn't look right, and that is looks to me very much like the cyanobacteria that would. Now, we haven't sampled. I don't know the exact results of this particular one, but I'd put a lot of money on that picture. So we are getting some bad things, and we're not alone, of course, but we are getting this blue-green algae and cyanobacteria, and we are trying to figure out why, relatively all of a sudden, this is becoming a problem. Very briefly, blue-green algae. Well, I noted earlier that we are not alone in our having this blue-green algae or these HABs. And if we look at the Finger Lakes overall, over the past years, we can see that everybody's got a chance to play, especially recently, but we've also had a big increase, hence why we're probably here and looking at these things now. So on the left-hand side, we see the 11 Finger Lakes are put out there, starting with Canisius on top, or the westernmost, and moving all the way to the downward in the slide, but eastward in the map to Skaneateles and Otisco. We're looking at who's actually had this stuff in the lake, anywhere from starting from 2012 until last year, 2018. If you stand way back, you can see that there's a lot of white space in the 2012 first 2 or 3 years. And then as we get to the last couple of years, 16, 17, and 18, there's a lot of color. What do those colors mean? White means nothing. We don't know. We didn't measure anything there. We didn't see anything obvious, at least. Blue means it's kind of suspicious, which sounds a little weird in a scientific sense that we would have a category called suspicious, but we do. This usually means that we think it's there, but we couldn't actually test it to confirm that. Green, in contrast, is confirmed sightings or confirmed observations. And in this case, you get a green bar if you got one confirmed sample, or you got 700 confirmed samples. Green just means, yep, you got something there, and we know it was that. Now, said most kinds of cyanobacteria are not harmful, but there are a few that are, and those are ones we worry about. And even those that are harmful don't always produce a toxin. And those that do produce a toxin can produce different amounts. And what we would like to be able to worry about are those stuff that are really the bad stuff. So the amounts when we actually go in and measure the amount of toxin. And if it's really high, then we get that red bar. So if you got a red bar, that means you definitely have confirmed algae there, and it's producing a lot of toxin, bad stuff. A lot of red in these last 2 years. Now we saw in 17 was the first time that all 11 Finger Lakes had confirmed sightings, and more than half of them had high toxin observations as well. 2018 was essentially the same. Canondice, one of the two unoccupied lakes, so to speak, part of the Rochester water program, they didn't have a confirmed sighting of the blue-green algae last year, but other than that, it was a carbon copy of 17, where virtually everybody got to play and playing a game that no one really likes, the game of HABs. 2 slides ago, I showed you the some pictures of Red Jacket and Ancuca Lake, and that's 2019, and it's back again. So we are hoping that it's not going to be as bad, but it's definitely, we're green again, as are most lakes this year. So we're going to get a little deeper into the data here and trying to figure out what's causing some of this. Now, those of all 11 Finger Lakes, we're seeing this, but the ecology of these lakes differs among the 11. Some of these lakes have a lot of phosphorus in them all the time, a lot of nitrogen, a lot of these nutrients, things like owasco and honeoy. And it's not surprising that we would see a flare-up or a pretty consistent bloom of these kinds of blue-green algae or HABs because of that. On the other hand, we've got lakes like Cuca Lake and Skaneateles Lake, which I talked about earlier, saying very clear water and low nutrients. These are descriptors and parameters that are not typically thought of as conducive for blue-green algae outbreaks. So it's a little odd that we would see these outbreaks in Skaneateles or Cuca Lakes. And when we're looking at all these lakes are trying to figure out what to do, but if we're really trying to look for root causes and then how those root causes can allow us to move forward with potential solutions, we have to get a better understanding of what's really going on. So one thing I'm looking at is kind of ratios. I showed you nitrogen by itself, I showed you phosphorus by itself. Both are these nutrients that can stimulate growth. But there's a big deal about how algae actually use this, and you have to have some of both for algae to grow. They can't grow with just phosphorus and no nitrogen or just phosphorus. They have to have some of each. And in the aquatic ecology world, we look at a specific ratio of this. And what these two lines are, looking at one's deep and shallow, and the other one's shallow, like we've saw before, we put together a line that's basically this index called 16. Anything is greater than 16, we call it phosphorus or P limited. That means that if you go to the lake and it's P limited, if you add more phosphorus, you'll get more growth. If you add nitrogen, you're probably not going to get any more algae growth. And you can add a bunch of nitrogen, you're still not going to get any more growth if it's in this top area, this blue line. In contrast, if it's N limited or nitrogen limited, so it's something less than that 16 to 1, you could add a lot of phosphorus and not see anything. But if you add a little nitrogen, you will see growth. Most freshwater lakes tend to be P limited, and so we talked earlier, there's something special about phosphorus. Nitrogen tends to run off the watershed very easily, so lakes tend to have a lot of nitrogen in them. Phosphorus, on the hand, tends to be very sticky. So even if you add a lot of it in terms of fertilizer, it's a lot more difficult for it to get from the land into the lake. That's one of the parts around that. There's more to it. But most freshwater lakes we thin is phosphorus limited. So you got a lot of phosphorus, you're getting a lot of algae. What we see here, and this is of just 2018, we see that those numbers bounce around, but you see them bounce around down to nitrogen limited, especially in the shallow waters, around late August and September, about the same time where we see where we observed so many of the blue-green algae outbreaks in Cuco Lake. This is interesting, and I'm not sure whether this is an interesting coincidence or whether this is a part of a bigger causative issue. But it looks like we're seeing times where nitrogen could actually be driving some of this. And this could be one of the reasons where Cuco and Skinny Atlas differ from the other lakes, which means that solutions to our problems, which is a common problem of blue-green algae, may have different solutions because we have different ecologies, perhaps. So, our threats, part of the talk, which we have been talking about, the threats, the big one is this increased observations of blue-green algae, or these HABs, these harmful algal blooms in Cuco Lake. What can be driving that? What can be causing that? In general ecology, we know that increased nutrient inputs to the lake. So if we get more agricultural fertilizer runoff, if we get land use changes, or we're dealing how we use very high intensity land or animal farming, that can all result in increased nutrients into the lake. We talk about sort of these point source or targeted inputs that could come from fertilizer or from other areas. We look at intense weather events, something that drives that has really like are very low wind, very calm days that are very hot. And if, for example, looking at climate change, could that increase not only the water temperature, the air temperature? Could that change the weather dynamics? So resulting in some cases of very low mixing environments. All of things could do that. We're looking at maybe nutrient shifts, so not just more nutrients, but the ratios of the nutrients that we have at any one time, and how that could vary among locations. So that last slide, a little geeky there, was looking at these N to P, or nitrogen to phosphorus ratios, and how that could be different in shallow waters than deeper waters. And we find in Cuco Lake and in most of the Finger Lakes, the shallow waters are near the shores, so we call those near shore dynamics. That's where we're seeing a lot of our blue-green algae outbreaks. Coincidental? Maybe, but that's what we're looking at. Another factor that can play into this, and I know that Tony and others will talk about looking at grazing issues. Grazing is sort of our fancy word for what zebra mussels and other things do when they eat the algae, or eat lots of algae. We call that grazing, just as a cow would graze on grass. Zebra mussels and other animals will graze on algae. So zebra and their evil cousins, the quagga mussels, they make their living eating algae, primarily good algae. And that results in clearer water, and which could be in some cases good, and other cases not so much. I also point out that they tend to leave the blue-green algae alone. Those big globules that these microcystis and other things make, zebra mussels can't physically get inside them. It's too big. The hamburger's too big for the mouth. And then even if they did, they really don't like the taste of it. So you can see where you get zebra mussels eating the good stuff and leaving the bad stuff, and there might be more nutrients for the bad stuff then. We even look at the effect of zebra mussels grazing on how toxic certain blue-green algae are. And we find that in particular, we've seen this in many lakes that are very low nutrient, like Cuco Lake and Skinny Atlas Lake, that have zebra mussels, that we do, when they do have outbreaks or these blue-green algae outbreaks, they tend to be very high toxic events. And of course, Keuka Lake was showing very high toxicity a few slides ago. So there are a lot of factors, and I'm very happy that Tony and Maria and others are going to be delving more into the details about this in just a bit. So, as we say, and I said this last year, the plot thickens. But hopefully not the water. There's a lot that's going on. This talk is to kind of give the basic of a little bit of the lake ecology, what that happens, some of the events that we've seen over the last 20 years or 30 years or so, how things have generally improved, but now we see this outbreak, and we're not entirely sure why. You also showed that we had a very strong sampling program, and we captured a lot of really good data, but there's a lot of data that we are missing. And I'm really excited over this past year, and you're going to see data from this past year, about how we've involved citizen scientists into increasing the amount of information that we are collecting. This is incredibly important. So now that we're getting more data, we're getting data that we didn't have. We're getting data from the streams, all these little streams and bigger streams that come into there. What are we actually dumping into the lake? What's coming in there? We haven't really known that in the past. Now we're starting to do that. That's excellent. And we are increasing the number of agencies and the intensity of which we are taking samples. So Tony, for example, is coming from the DEC, and they're doing a lot there. We're partnering with a lot of different agencies to get great information and looking at different ways. We've got a unique problem, and I'm really excited because we're attacking this from a variety of ways to try to come up hopefully with some maybe unique solutions. And the rest of the night, you're going to hear about a lot of the details of all this exciting stuff. So again, I'm sorry I couldn't be there. Hopefully this gives you a little idea of where we've been, a little idea of how the system works, and gives you a decent foundation from which to put the rest of the great information you're going to hear tonight and solidify that in your head, and we can walk out of here with great plans, great ideas that will match the enthusiasm that you're already bringing. So thank you again.